Hello, so let's talk about another vector operation called the cross product. A cross B, that's our cross product operator. This is also called the vector product. It does return a vector, unlike the dot product, which returns just a number, a scalar. The cross product returns another vector. And so here's how I remember how to calculate the cross product. I set up what's called a determinant, and it's sort of a bit of a kinesthetic method for me, how I remember it. I write I, J, K here, and AX. And this is going to give us our answer, which will be a vector. There's not going to be enough room there. So I know it's going to be a vector, so I'll get it set for that. All right. So the way you solve this determinant, the way I do it, is you cover this up. Okay, and this method will write out the definition of the cross product for us. All right, so the way I remember the cross product is I cover up the component I'm interested in. So let's start by finding what goes here for I. We cover up the column of I, and it's this times this minus this times this. So that's A, Y, B, Z minus A, Z, B, Y. Look across like the cross product. What do you know? All right, and continue like that. So now we're going to cover up the J component, the J column, and it's this times this minus this times this. AX, BZ minus AZ, BX. Okay. Now we're going to cover up the K column for the K component, and it's AXBY minus AYBX. AYBX, like that. And one more thing is that the I is positive. No need to put a plus there. It's implied, right? But then the J is negative, and the I and the K is positive. Okay, positive, negative, positive, and you write the rest fill in the rest using this determinant. And that's how I do it. You could just memorize this, what I've written out. This is the cross product. It shouldn't be that hard to memorize, but I am terrible at memorizing things. So that's our cross product. Now, we also know that this is a vector, right? Because it clearly is a vector. But if you take the magnitude of the cross product, the vector that comes out of it, take the magnitude, well, that is equal to A, the magnitude of A times the magnitude of B times the sine of the angle between them. And so very similar to how we had cosine was the magnitude of A, we had the dot product was the magnitude of A times the magnitude of B times the cosine of the angle. Here is the sine of the angle. And this relationship is very useful for solving problems. Let's do one similar to one we've done in the past for the dot product, but this time let's pick a problem that helps us, that uses the cross product. So a problem could give you two vectors. Say, here I go. So two vectors I made up. And it could ask you to find, well, this one's weird. It could ask you to find the component of A that's perpendicular to B. Okay, so let's look at it. Now, this isn't exactly how they're drawn, but, well, if you had them represented in space, so floating out in space like this, you could always walk to the side so that you looked at them and they looked to be flat. If that makes any sense. You could always arrange them so that you're looking at them side by side like this. I won't try to put in the what they actually look like, the I's, J's, and K's, but here they are floating around. And what they're asking for is the component of A that's perpendicular to B. And that would be this right here. If you watched another video, we found this component, the component of A that was in the same direction of B. Now we're finding the component of A perpendicular to B that's also in the plane of A and B. So this makes a right angle, right? And this here, let's label this as the angle between A and B. So what we're looking for is this right here. Not really sure what to call it, A1 or something. So that component. Well, we know that this length, the length of A, is the magnitude of A. So if we knew theta, we could write that A1 is equal to A sine of theta. Now, we don't know theta, but see, there's something very similar to A sine theta up here in the cross product. We could calculate the cross product of A and B, and then use that to find theta and plug it in here. Or better yet, we could rearrange this to solve for A sine theta, since that's what we need. So looking at the cross product right there, if I divide B from both sides, I get that the magnitude of the cross product divided by the magnitude of B is equal to A sine of theta. And that's actually also equal to A1. So all we have to do is calculate this. And it's a bit lengthy because the cross product is this long definition right here. Now you remember, you could just memorize this, but my method is to use the determinant and fill it out. All right, so let's find what the cross product is. Let's do actually plug in numbers this time. So here we go. We've got AY times BZ. So AY is 4. BZ also happens to be 4. Minus AZ BY. So AZ is 6. BY is 2. That gives me my I component. And then minus AX BZ. AX is negative 2. BZ is 4 again. Minus AZ, which is 6. BX, which is 2. That gives me my J component. Plus AX is negative 2. BY is 2. Minus AY, which is 4. Times BX, which is negative 1. And that gives me my K component. So calculating this, we've got 4 times 4 is 16, minus 12 is 6i. Okay, minus, this makes negative 8, minus negative 12 is negative 20. So minus negative 20 means plus 20 in the I hat direction, or J hat direction, plus we got negative 4 minus negative 4, so negative 4 plus 4 is 0. Oh, look at that. 0 in the K hat direction. So this is A cross B, but what we want is the magnitude of A cross B, right? So the magnitude of this vector, or rather, let's just continue solving. So A1 is the magnitude of the cross product divided by the magnitude of vector B. So the magnitude of this vector is the square root of 6 squared plus 20 squared plus 0 squared, if you like, though of course it's unnecessary, divided by the magnitude of vector B, which is the square root of, looking up at vector B, negative 1 squared plus 2 squared plus 4 squared. Calculating all this, about 4.56. And so that is the component of A that's perpendicular to B. Okay, so there is an application, sort of the cross product. Now, we will have physical applications of the cross product, just not yet.